let's go ahead and get started. Okay. So the solubility product constant of Ag2CO3 is 6.2 times 10 to the negative 12. What is the concentration of silver ions in the saturated solution? And in the saturated solution of AgCO3. So we're going to do that. Let me see here real quick. There we go. Okay, so first off, what is our equation going to be? Is what we need to look at here. Oops. So for our equation, we're going to have our Ag2CO3 whoops, have this, and then go ahead and get an arrow. We can use, here it is. That's the right one. Okay, so that, and that's going to separate out into 2 Ag plus, whoops, plus our CO3 2 minus. All right, cool. So now we have that. So now we need to get like a rice table going with this. So it doesn't matter what's on this side because I didn't put this in here, but because this is a solid, so we don't need that. And then this one is going to be off, and the other one are both aqueous, so that's why we need them. But so it doesn't matter what's over here because it's aqueous. So we're just going to go ahead and back here. So yes. Oops. Okay. So initial, we don't know that change. And we do know that because we can figure that out. So we know that with the change, we are starting out with this over here on the left, so it's going to have to decrease over on this side, which means it's going to have to increase on the other side. So we're going to have plus 2x of the Ag plus, and then we're going to have plus x of our CO3 here. Okay, so then we know the equilibrium, we're just going to go ahead and make that just straight of our 2x and our x here. So we can use our KSP equation to find this. We have KSP is going to equal the concentration of our Ag plus and the concentrate times the concentration of the CO3 2 minus. So we're going to take this and we can go ahead and plug in what we do know. So they gave us the KSP. So we know that. Oh, you are right. I did leave out the 2 for this. Good catch. So it's going to be 6.2 times 10 to the negative 12th power. I could have copied and pasted that. That's okay. And that's going to be equal to 2 times Ag plus. So we're going to get that from here. So 2x times this over here. So multiplied by x. Okay, so whenever we multiply, yes, I'll be posting the key online. And let's see, looks like we've had new people join. If you haven't yet, will you please send me your full name and your UID just in a private message on the chat? But yes, I will be posting the key. And let's see. It's gonna have this here. So then we know that this, we will say out, thank you, is gonna be, oh, I put that in the wrong place. That should be squared. And then that's gonna make this squared. Okay, so we know that when we do that, we're gonna have our 2 squared. So we're gonna have 4, apologize, I'm turn off my volume here. And so that's our 4. Then we have x squared, so we are gonna have x squared here times another x, so that's gonna be x cubed. So, whoops. So we have that. So whenever you solve all of this out, you end up with x equals what? It's going to be capitalized, that's fine. All right, so this x is going to end up being equal to, when you solve it out, I'll go ahead and do this one because that way I have time to get through more complicated ones. 1.6 times 10 to the negative 4. Okay, and then it's KSP, so you don't need, or you do need unit spreads because this is, x is going to be for that. So we're trying to find the concentration of the silver ions in the saturated solution. So the concentration, how would you put this in a calculator? Okay, so with that you would, because you have the 4x cubed here, you would type it in, here, go ahead and do that. You would type it in like this. You'd have this number. So you're gonna have that. And then you're going to have to, first off, divide by 4, because you need to get x by itself over here. So I'm going to have that divided by 4. And then you're going to take all of that, and you're going to take the cube root, because then you're going to have this equals x cubed. So if your calculator probably does not have a cube root, what you're going to do is you're going to put it to the 1/3 power. So that'll look like this. And then you get your answer that way. So we're trying to find the concentration of our silver ions, which we have right here. And we know x, so we just have to solve that. So whenever we do the 2 times, 2 times this, then we'll find our answer for that. So our concentration of our silver ions Do not get that answer. Let me solve it again, see if I messed up when I did it before. It happens. Okay. So we're going to do that is also what I got. Ah, that's probably what the difference was. Let me do that again. See if that's what we. Yeah, that's what the issue is going to be there. Yeah, so where I left out the put 2 in sub 12, just a typo there. That's where that came from. So yeah, you're all good. Thank you guys for catching my mistakes. That means you're paying attention to your learning, so that's good. Okay, so we had, we're trying to find the concentration of this. So that's going to be equal to 2x, because we have that right here. And we already have x. So 2 times this right here. And I'll get your final answer. So you should end up with 4.32 times 10 to the negative 4th. There you go. Okay. What is the solubility of aluminum hydroxide in 0.25 molar solution of potassium hydroxide if the KSP of aluminum hydroxide is 3.7 times 10 to the negative 15? So we're going to once more, we need to have our equation going over here, and we're going to have a rice table again. So I'll go ahead and set that up. Okay, so for our reaction, we're going to have our aluminum here. And that is going to, let's do my arrow here, dissociate into aluminum and hydroxide. So we're going to have Al3 plus and also we're going to have 3 OH minuses. So, whoops, that is not an H. There we go. So we have that. So what do we know? Once more, this is going to be solid and these are going to be aqueous. So we don't really, what's over here doesn't really matter because we're doing KSP. So our aluminum hydroxide here, we have our initial that they gave us in a solution of this. So whenever you separate KOH out, it's also going to separate out into ions, correct? So it's going to equal, you're going to have K pluses, and you're also going to have OH minuses. Well, OH minuses, since those are the same as what you have in the other, you have to include that in that. So we're going to have some OH minuses. Okay, and because we have 0.25 molars here of this, whenever it separates out, it's a 1 mole to 1 mole ratio. So it's still going to be 0.25 molars of this over here, of the OH minus. So we have 0.25 molars of OH minus to begin with. So we're going to have to include that as our initial over here. So we have 0.25 molars. Then our change, we know from looking at this, obviously we're going to have to get rid of this because this is what we're starting with. And so 1 mole to 1 mole ratio, so this is going to be plus X. And this over here is going to be plus 3X because of this coefficient of 3 that it has out front there. So plus 3X. So at equilibrium, we're going to have X over here, but then over at this one, it would be 3X plus 0.25 molar. But what you typically do in pretty much anything, and he's always going to have it this way in your exams, is you're just going to ignore this 3x right here because it's small enough it doesn't matter in comparison to your 0.25 molars here. So this is just going to be 0.25, and that makes the math a whole lot simpler. So we're going to go ahead and we can use our KSP equation. So we have our KSP equation. Start another window. It's going to be the concentration of our Al3 plus times the concentration of our OH minus to the third power. So we can go ahead and fill in what we know. They gave us the KSP over here, so we can go ahead and take this right here and plug that in. And that's going to be equal to what we know for aluminum, so X times 0.25 molars, so 0.25. We don't have to worry about units with KSP here. And that is going to be cubed. Oops. Sorry about that. That's the wrong button. So we're going to go ahead and you can solve that for X now is what we're looking for. And so you can, to make that simpler, you could go ahead and figure out what this 0.25 cubed is going to be equal to. Okay. So if you go ahead and solve out your 0.25 cubed, I already have that worked over here. You end up with 0.015625 x equals this. So to find x, all you're going to have to do is divide this by the other number. divide, whoops. So you're going to divide that by this. Okay. And so when you do that, what do you guys come up with for x? And I'll give you a minute to solve. Perfect. That's what I came up with as well. So it's going to be 2.368 times 10 to the negative 13 times 10 to the negative 13. So then you have that. And that is going to be, yeah, mass red solubility of the aluminum. So you figured out how much aluminum you're going to have in this. And because aluminum is equal to X, this is equal to the concentration of aluminum. So that's all you needed. There you go. Okay. What does it mean when a reaction is spontaneous? There's a word in there. That's weird. So a spontaneous reaction will proceed without any outside interference or help. Yeah, I have a typo there. So there's that. We're going to define entropy. Sorry, that's so weird. That's strange. Okay. So entropy is the degree of randomness in a system. And that's going to be delta S. I don't have a delta in here yet. Think of it. See if I can see one from here. Aha, here's delta S. There we go. So we have delta S. And then define enthalpy. And enthalpy is going to be, the total heat of a system. And that is going to be delta H. And then okay. Go ahead and keep going. What are the 3 laws of thermodynamics? So we're going to look at the first law here. Oh, wait. I think I actually have this in here. First law, also known as law of conservation energy, states energy cannot be created or destroyed in an isolated system. That's right. Give you guys a second to write that down if you'd like. Actually, if you have it pulled up in a document, because I forgot I had this white out like that, it's probably still there, and you can just maybe. There we go. Our second law here Second law of thermodynamics states that the entropy of the universe is always increasing. The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. And then absolute zero is 0 Kelvin. If you didn't remember that, 0 Kelvin. Okay, I'll give you guys a second to write that. All right. So with this, we're going to look at the direction of a reaction and what that's going to mean for K, G, and E here. So I think I already have all these here. Yeah, I do. Cool. So we're going to talk about when it's spontaneous, non-spontaneous, and whenever it's at equilibrium. Are these ones here? Oh, these are too. So cool. So whenever it's spontaneous, these values are like going to reflect that in a certain way. So what is that going to look like for E? I'll go ahead and I'll do the first one, and then I'll let you guys guess after this. So for E, it's going to be positive. And then your E cell here and your G value are always going to be opposites. Like if one's positive, the other will be negative. They're always opposite like that. So this one here is going to be negative. So then with that, we have that. So then our K value is a little bit different. Our K value, if it's going to be if it's greater than 1. So if our K value is greater than 1, that's going to mean it's spontaneous. And so these are kind of things you can look at to see whenever you are solving different problems throughout. So now if E, whenever it's spontaneous, is positive, what do you think E is going to be whenever it is non-spontaneous? Negative, perfect. So it's going to be negative. And if E is negative, what does that mean for G? So what do you think it'll be? Positive, negative, some random positive, perfect. Okay, so what do you think K is going to be? Oh, well, I can give it to you. It's going to be less than 1. So you see these are all opposites for spontaneous and non-spontaneous here. And your E and G will always be opposite of one another. So at equilibrium, so not whenever it's spontaneous or non-spontaneous, this is going to be at 1, which makes sense because I mean, if it's less than 1 and greater than 1, depending on whether it's spontaneous or not spontaneous, it's got to be 1 at some point. That's when it's at equilibrium. And and that's kind of the same way you can look at it with our E and our G values. Well, if it's negative whenever it's spontaneous and it's positive when it's not spontaneous, well, what's in the middle there? That's 0. And then same thing for here, but opposite ends up being 0. So do that. And these are kind of like I said, those are the clues you can look at to figure things out as you're solving problems throughout. Okay, so if you look, actually, so before we do this, let's go ahead and go to the last page. Give you your formulas. I guess we did already do something formulas, but that'll make life a little bit easier. So we're trying to do these, and I'm like, what's the formula for this? Y'all actually know what I'm talking about. If you don't remember. So I'm gonna look at formulas here. So what are our formulas going to be for solubility product and reaction quotient? We already did this. For solubility, we have our KSP, and that is equal to the concentration of the products all multiplied together. And then we have Q, and Q is equal to products over reactants. The concentration of products over the concentration of the reactants. And remember that K and Q are the same thing, except for because Q is the reaction quotient, but K is the reaction quotient at equilibrium. So if you have all of this but at equilibrium, that's going to be K. Okay. Then, so we have Q if it's concentration. We're also going to look at Q if it is with the pressure of gases. And so that is going to be, it's still products over reactants, but you have to write it a little bit differently because we don't have a fancy symbol that universally means react or that means the pressure like it does for concentration. So you have the pressure of A to the A power times the concentration, or not concentration, the pressure of B to the B power. And then you're going to have, whoops, all of that over the concentration, keep saying that, the pressure of C actually, I normally write this the other direction, so I'm going to switch this. I had it written down a different way before, but I normally write this the other direction. You can write it either way you want, but it just depends on how you've written out your equation. So I like to think of it as this, but C and D. So put the pressure of C to the C power, and yeah. So if you have all of this, and this is going to be like if you'd had an equation and it was like a to the, or it was like a, whoops, it was like little a, big A, plus little b, big B. Was that? I can write that up for you. So that would be if you had the equation and it looked like this. Whoops, that's supposed to be plus. And that equals C plus D. So that's what that's from. Okay, then we're also going to have, and like I said, this only works for gases, obviously, because it's pressure, that last part there. Over to thermodynamics. So if we have delta H, I think, no, it's probably, yeah, there we go. So we have delta H naught here. So for delta H naught, that's going to be equal to the sum. You get that somewhere. See if that one's here. And that's going to be equal, yeah, to the sum of H products minus the sum of H reactants. Okay, and that's really what the equation looks like for delta S naught and delta G naught as well. You remember? Delta S, it looks the same, you just change out the letters. And for also for delta G. And there's most of those. There's another equation for delta G also that we can use. And that is going to be equal to negative RT times the natural log of K. And then if we're solving for delta G, but we know delta G naught, then it's going to be delta G naught minus RTK, or not RTK, RT times the natural log of K. So that, and then on to the ones for electrochemistry. Go closer so you can still see those. Okay, so for electrochemistry, we're going to have a delta equation for delta G first off here. And that's your negative N times Fe naught. We're just going to do this and do that. We're going to have one for E cell And that one's going to be E naught. So and it's going to be cathode minus anode. And then we're going to have E equals E naught minus 0.0592 over N times the log of Q. And those are going to be our equations that we use a lot. And in this, if you don't remember, that was like the moles of the electrons. F is Faraday's constant, which if you look right on the page right before that with the table, it has Faraday's constant on there, which is the 96,500 C per mole E minus. And yeah, you know the rest of that. G, Gibbs freeze energy here. Okay, so we're going to go ahead and go back up to what we were working on. Let me see. We're solving for, that's right, delta E, delta H, delta S, and delta G. So I'm going to go ahead and just go ahead and steal these equations, or one of these, I guess, before we go back up there, make life easier. So, right here. Solving for delta H first. There's our equation. I guess we're all in bold here. We don't need that. There it goes. Okay, so we have that equation. So we need to fill that in. And based off of our table that we have, we can go ahead and do that. So we're trying to find delta H here. And so we're going to look at delta, or not delta, but we're going to look at the H naught of the products. I didn't put the naught in there, but that goes on all of those actually. If you didn't know that, that goes on all of them. And so you should have those numbers in the lovely table. And see under the where it says delta H, you're going to look in that column to find those. So we need of our products first. So we're going to look at NH4NO on here. Find delta H, and we're going to see that that is negative 365.6. And then that's all of our products. So we're going to subtract it from, or we're going to subtract all of our delta H's of, or our H naughts of our reactants. So first we have NH3. We find that on there and see that it's negative 46.19. And the unit for all of these is kilojoules per mole, so I'm not going to type that out every time right now. And then we're going to have to add of the H naught of the HNO3. So we find that on there, and it's negative 134.3. So you're going to solve. Just go ahead and like type this in the calculator straight up how it is. And then you'll be able to find your H naught here. Find your delta H naught. And that is going to be what? When you solve that out, what do you come up with? Oh, let me get my charger real quick before this dies on me. There we go. Okay. Perfect. Negative 185.11. That's exactly right. If you're being a stickler for sig figs, just keep one of the ones. Just keep one negative 185.1 because this only has one sig or one sig fig after the decimal, and so does this one. So we would just leave it with that. So it's negative 185.1, and that's going to be kilojoules per mole. Oops. Per mole. So now we're over to doing delta S here. And we're going to do the exact same thing except for with S. And you're going to go to your table, find your values once more. And so we're going to get this. Okay, whoops. So first off, just like before, we're going to go and find our products. So it's going to be first this. Okay, so we can find our NH4NO on the table and see that's 151. So we'll have 151 minus all of the reactants. So we go find NH3 on the table. And we find 192.5. And then we're going to add the HNO3's S value. And that's going to be 266.4. Okay, so whenever you do the math on that, what do you come up with? Wonder if I can get that to come back up here. There it goes. Okay, now we have delta G up here with the rest of this. Only one line now. There we go. Okay. The recording is going to be on, I'm going to be posting them on YouTube, but there'll be a link to it on my website. So it will be there. Okay, so we have finding S value here. Oh, yep, we have an answer. Negative 307.9, perfect. Joules per mole K. Yes, I have a question. Will you be posting the keys for the other worksheets in chapter 3? And yes, I will. I'll get all those up there tonight so you guys can have them to study. Okay, now it's delta G here. So for delta G, we're going to do the exact same thing once more. Go get our values from the table, solve those. So we look at our table, we find our NH4NO3 once more. and we go find our delta G, and we find negative 184.0. And then we have to do all of our products. So NH3 is negative 16.66. And then we're going to add HNO3's delta G, or no, delta G not value. And that is going to be negative 73.94. So you're going to add all those up. And you're going to solve that, come up with negative 93.4. And that's going to be kilojoules per mole, because that's the unit they gave us. I have another question here. Do I know how the test will be formatted? I'm not sure how your test will be formatted. He hasn't put that in any announcements or anything. I'm not sure what that'll look like at all. Hopefully, he should give you more information on that tomorrow. And I emailed him earlier today, and he didn't answer me yet, which was just a couple hours ago. And as you guys, I'm sure, have all seen, trying to do college from home, or for him, trying to do work from home is a bit strange. So give him time, he should get it to you. Okay. Let's give the delta G here. Okay, so we're going to look at those answers above to answer that. So is this reaction be endothermic or exothermic? Okay, do you think it's be endo or exothermic? Looking back at this. Exo, perfect, because our delta G is negative, meaning it's, wait, that's energy. Heat there. Since this is negative, that means their delta H, that means it's releasing the heat, making it exothermic. So that's not gonna work. What we're gonna do. There we go. So it's gonna be exothermic. Then is the change in entropy favorable or unfavorable? So you can look at that. So it's gonna be, you think it's favorable or unfavorable? And that's based off of your delta S value, if you don't remember. That's right, it's going to be unfavorable. Perfect. And that is going to be right here. And that's unfavorable because a negative delta S value is unfavorable. Positive delta S value is favorable. And is it going to be spontaneous or not spontaneous? And remember, that's based off your delta G right there. Spontaneous. Yes, perfect. So yes, it is spontaneous. Yes, because our delta G is positive, or is negative, I mean. I'll go ahead and put that on here for you. Delta G naught. Okay. Using the thermodynamic data provided in the table, calculate the equilibrium constant for the reaction at 25 degrees Celsius. So they gave us this. So try and find equilibrium constant. All right. So our equilibrium constant, remember, is the K value. So let's see here. That's not what we did above here. No. Okay. So this is one of the equations that we talked about earlier to find our delta G value. So once more, we're going to have to get that equation. Copy and paste it up here. Just right here. Find that. Okay. So just gonna make this cool. Okay. So we have that. So looking at this, we'll have our equation. Just one more. It's more in bold for some reason. Okay. So first off, we need to figure out what we know. We know that we can go ahead and fill in what we do know. We don't know delta G. Yeah, they didn't give us that. What we do know, we know R, because that is a constant that we always use. And so actually, let's go ahead and rearrange this in the format that we're going to use. Because that'll make it easier for doing math later, in my personal opinion. So we go ahead and add RT to both sides and have this as plus RT. Then, because we're trying to find K, that's what we're doing. And then to get rid of natural log, that's where you do e to the negative, but we're not going to do that yet. So just going to leave it like this for the time being, and then we will do that in a minute. So we're trying to find this. We don't know delta G yet, so we can't do that yet. What we do know, we know R, because that's the constant I was saying a second ago. And that is, where did I write it down? Here it is. Okay, that's the 0.008314 kilojoules per mole K. Per mole K. So in that case, Kelvin. And so then we know our temperature to replace T. So you can go ahead and put that in because it gave us this, and we add your 273 to turn that into Kelvin. You get your 298 Kelvin. So we have that. Now we need to find our delta G in order to solve this. So just like before, like we did delta G up here, it's going to be that same process again to get our answer. Oh shoot, I typed that wrong. I apologize, guys. Okay, this is not plus, that is divided by negative. So that's divided by. I apologize, guys. So we have that. We're going to go ahead and find our delta G. I'm just coming down here a little ways and do that. So our delta G equation, we have that. And to find delta G, I'm going to do just like before, products minus reactants. So we're going to have the products here. So we have H3O plus, find that on here, find our delta G value in our table, just negative 39. And then we're going to add for HCO3 minus, which is our negative 587.06. And then we're going to subtract our product, our reactants. And so we have CO2, so negative 394.359. And then to add the other one, so H2O, go ahead and add that. And because there's two of the H2Os, we're going to have to go ahead and multiply that by 2. So 2 times H2O here. And so for H2O, our value is negative 228.57. So you're going to solve all of that. And you'll come up with your answer of 225.439. Because that's not our final answer, I'll go ahead and keep all of our digits here. Yeah, 0.439 kilojoules per mole. Whoops. And so we have our delta G. So we can go ahead and plug this in up here for this delta G right here. So now we can figure out what this is going to be. So we're going to have the natural log of K. And that is going to be equal to 90.929 90.929. And so we can look at our units and we see that, oh, I forgot to close that parentheses. But so all of this is on the bottom of the thing. So we see that we have, I wonder if, okay, cool. So we have a kilojoules per mole here. We have kilojoules per mole here. And then we have our Kelvin here. And we have our Kelvin here. And see, so this Kelvin's on the bottom of a fraction here. So that's why those two cancel each other out. And the other one is not. Or I guess they're both under the big one, but this is under a little one as well. So I'll flip it around. So that gets rid of all of our units, as we can see here, because our K value doesn't have units. So that's going to equal that. So when we just want to go ahead and find K, we're going to have K equals, oops. And it's going to be e to the power of 90.929 there it goes. Okay, and then you're going to solve that. And you're going to have K equals 3.09 times 10 to the 39. D. Yeah, there you go. Okay. And so we're going to have, let's see, that's all you need. Let's see. So to the 39. Oh, sorry, got distracted there. So there's your answer for that. And go ahead and continue. And get rid of part of this so we can, y'all can still see some of that. Okay. If delta G naught is 248 kilojoules per mole for the following reaction, what is delta G when the mixture contains 0.4 atm of CH4, 0.6 atm of O2, and 1.2 atm of CO2, and 0.8 atm of H2O? So we need to find delta G here, or not delta G, yeah. So first off, what we're going to do is, wait. Okay, so they gave us delta G and not, and we have to find delta G. We have an equation we talked about. I should have put this closer to the top, but I didn't, so here we are. And we're going to use this equation here. And sounds weird again. Okay. So here's our equation. And so we're going to figure out what we can fill in here. So we have delta G. We don't know what that is yet. That's what we're solving for. And they gave us delta G naught, so 248 kilojoules per mole. Oh, that didn't work right. Okay. Okay, so and then we're gonna have that. We're gonna subtract R. And I don't want to type R again, so I'm gonna go steal it from up here. Okay, so here's R. And so we have R there. Then we're gonna go ahead and okay, so since they didn't give us a temperature, we're going to assume that that's standard, and it's going to be, once more, our 25 degrees Celsius or 298 degrees Kelvin. And we're going to multiply that by the temperature. So 298 Kelvin. And we're also going to multiply that by and so since we're going to do that, okay, and then we have the natural log of Q, which we don't know yet. And we have to, okay, that should be Q because we don't know if this is at equilibrium this time, I guess. So that makes it Q, which those are kind of interchangeable. And so we have to find a reaction quotient. And so like we talked about over here, the reaction quotient is going to be Q equals this equation right here. But that would be, oops, not too far. So it's this right here. But instead of putting like this, we would have put in these different things. So like this would be CO2 to no power because it doesn't have anything in front of it. And then we would have E to the, this would be H2O. Whoops, I don't know what I'm doing now. Okay, and that's going to be to the second power. This will be CH4 to no power. And this is going to be O2 to the second power. Okay, so we can go ahead and solve that. I do that. Here we go. Okay, so with that, we're going to go ahead and plug in what we do know. So we have the pressure of CO2, which they gave us right here, so 1.2 atm. And since they're all the same unit and they're going to cancel out, I'm just not going to bother to type them in. H2O is going to be your 0.8 here. Then we're going to divide that by pressure of CH4, so that's our 0.4 atm. And that's going to be times our O2, which is 0.6. And this is, I didn't write that in. This is what Q equals. So when you solve for Q here, you can do all of that and you end up coming with 5.33. And then if we want to, we can go ahead and do the natural log of Q, so we don't have to do that in a minute. Just go ahead and take the natural log of all of this. So you don't have to do it up there if you'd like. It just depends on your calculator and how you like putting things in. And that would make this the log of Q, natural log of Q. Q is going to be equal to 1.673. So we can go ahead and take this and we can plug it in for this here. Okay, and then you can go ahead and solve delta G. You've got everything you need. And come with your answer there. Oh yes, I didn't put that in here. I didn't type that in. I did do that before, I just didn't type it just now. These are squared. Yes, those are supposed to be squared. Good catch there. Okay, so we have our delta G is going to be equal to this when you go ahead and solve it all out. And it's going to be 243. And it says I had 0.855, but you'd probably go ahead and round that to 0.9 just by kind of looking at the values you've got there. So it's probably a good idea. And you could honestly probably even put 244. And so that's what you got. That doesn't have a unit. This was Kelvin. Okay. So you can kind of get rid of part of this. Like you don't need your Kelvin anymore. Those canceled out. And then kilojoules per mole minus kilojoules per mole. So then that ends up with those units being equal. Don't forget, if you have like this one was in kilojoules and this one was in joules or something like that, you would have to go back and change one or the other to make that equal. Okay. So we're going to give the oxidation state of manganese in these compounds. And so if you remember how to do this, remember the oxygen is always going to be equal to -2. Whoops. And so we can kind of use that to figure this out. So oxidation state of manganese, we're going to figure out what that equals. So we have 2 oxygens at -2. So 2 times -2, we have -4, and the overall charge is 0. So 0 is going to equal that. And so we're going to go ahead and just switch the sign since the overall charge is 0. We'll make that 4. And then we're going to have this one, manganese. See what that's equal to. So this time we have a charge of -1. And so our overall, that's going to be our overall charge. Our value for oxygen is -2, like always, for oxidation state. So -2 times 4, we have -8. But then since your overall charge was 1, you can go ahead and take 1 off that and make it -7 and just flip it around that way. Probably did it. That's 7. Oops. Okay. And put your plus signs in there. And that's your oxidation states. Okay. Labeled oxidation and reduction portions for the following reaction and to determine which is the oxidizing agent and which is the reducing agent. So to do that, we are going to go ahead and so we can look at this and we see, so since oxygen's by itself there, so we don't really do that. So hydrogen is going to be -1 here. So the second one means negative, and it's pretty much always either plus or -1, usually -1. So we have -4 there, making the carbon +4. Okay. And if we go look at the carbon over here, it is also going to have to be +4. So that doesn't really matter. But then when we look at the hydrogen, which is the one that's actually important this time, we look at that, and since we decided it was -1 over here it's going to be positive because it's first. And we have a -2 for oxygen, making each of the hydrogens +1 since we have 2 of them. So that means our hydrogen increased here. So this is going to be our oxidation is going to be this right here. We'll do that. I'll highlight that again. Did that the other day and that worked out. So this is going to be our oxidation in blue here. And then, so that means this will have to be yeah. So yeah. So that means that this will have to be the reduction here. Go ahead and do that in red. Show that. And there we go. Let's see. Oxidation. And so if it's the oxidation one, that means it's the reducing agent because it's the one that causes the reduction of the other one. And so then for the reducing, the one that's reduced, I guess the one that is oxidized. The reduced. So the one that's reduced is the oxidizing agent. So go ahead and color code those for you as well. There's that. So yes, so if you just went ahead and took these and separated them out, your CH4, then your little arrow to your 2HO2, that would be the oxidation portion of the reaction, and your reduction part would just be this center thing right here. So cool. All right. We're going to balance this redox reaction in acidic conditions. So what we're going to do with that, we have to separate out into its two pieces. So we have sulfur and manganese look like our main components here. So we're going to go ahead and we're going to have this. It's 1/2. I don't know why this is being weird like that. Okay. And then we're going to have, that would be the other half of the sulfur one. Oh, shoot. There we go. Okay. Then we'll have this middle part. Let's be the other one. Okay. So, you need to go ahead. This whole thing is going to be weird. Let me fix this real quick. Okay. I think that fixed it. Okay. So, oh, that also would mess this up. Sorry, guys. Let me fix this real quick. And get this again. Okay. Okay. So we can go ahead and start solving these. So looking at these, we see we have 1 sulfur on each side. That's perfect. Good to go there. But we have 3 oxygens on this side and 4 on this side. So we need to add a water to this side so that it has the right number of oxygens. So we're going to have this, and we're going to add H2O. Whoops. So now we have an equal number of oxygens on each side, but look, we have 2 hydrogens over here and we don't have any on the other side. So we're gonna have to go add 2 H pluses over here. Oops. So we're gonna add those. Then we can look at this and we see, so our charge on the left over here, we have 0 plus -2. So we have overall charge of -2 over here. And over here we have -2 and +2, because 2 times your +1 here. And that's going to cancel out to 0. Since we have -2 over here and +2 over, or and 0 over here, we have to make those equal. So we're going to have to add 2 electrons to this side. So we're going to add 2 E minus. Okay. So then we've solved that half of the reaction. So now we're going to have to come do this other side of it. So we have 1 manganese on each side. We're doing good with that. So we don't have to worry about that. So we're going to take care of our oxygens first. And remember, you have to go in the specific order with this. Okay, so we have 4 oxygens over there, so we're going to add 4 waters over here. Okay, so we add our 4 H2Os. So now we have 8 hydrogens over here and none over here. So we're going to add 8 hydrogens. All right, so now we're going to go ahead and look at our charges. So over here, we're going to have +8 -1 charge, so we're going to have a +7 charge. Over here, we have a +2 and a 0, so we have overall +2 and +7. So this means this side is going to have 5 more charge than the other, so we're going to go ahead and add 5 electrons to balance it out. So we're going to add our 5 E minus. Okay, and so that balances out this one. So now we're going to take these 2 equations, and I forgot to leave that other one here so you can see the process there. Do that. That's what this one started as. Okay, so now we're going to take these 2 equations and we can go ahead and put them together. So what I like to do is I just like to take this, go Control C, E space plus space there, and then we're going to take the first half of this reaction. And then our lovely arrow, and then the second half of the reaction. And then we have this. All right. So now we're going to take this whole thing and balance it. So we can see what we've got here. And okay, so this is what we're working with. We have water on both sides. So look, we have 1 over here and we have 4 over here. Oops. So we can go ahead and get rid of the water over here and make this one only 3 waters. Okay, then we can look at our electrons. So look, we have 5 over here and 2 on the other side. So we can subtract 2 electrons from both sides. And so now we've subtracted our electrons. Okay, so now it's even. Hydrogens. So look, we got those on both sides too. So we can subtract 2 hydrogens from both sides. Okay, and that's it. Now everything is even on both sides. So we should be good. And so if you go back and you could go and check everything and it should all balance out. have your balanced equation there. And so if you did the same reaction, but it was in basic conditions, go ahead and give you an example of that. So if it was in a basic solution, then once we got to this point, we would take this and so we're going to take this and then we would go, it's basic, so we cannot have these hydrogens over here. Like, that's not cool. So we're going to have to add OH minus to turn those into waters because it's basic. So that means we're going to go ahead and I already have that. So we would take this, we would add 6 OH minus to each side. Okay, so we're going to add that to this side and to the other side. Okay, and so whenever we do that, this OH minus is going to react with this 6H plus, and it's going to form 6 waters. So then it gets rid of this, and it's going to form 6H2O. And we have 3 waters on the other side. So we're going to be able to go ahead and get rid of 3 waters on each side. So minus 3H2 over here and minus 3H2 over here. Oh, I forgot a step. Dang it. Okay. Okay, we're going to have to go back to here. You should not have electrons left at the end. That's why I realized I messed up. So on this, you're trying to balance out your electrons to actually balance the equation. So we have 5 on this side and 2 on this side. So we're going to have to multiply that to get rid of those. So we're going to multiply this side by 2. Whoops. And we're going to multiply this side by 5. To be able to get rid of that. So we're going to have, okay. So we're going to end up with this right here. Okay, so we have our 2 H2Os, we have 2 of those, we have 10 of those, 16 of those, 2 of those, over here multiplying by 5, and get rid of that. Okay, so we have 5 of those, 10 of these, 10 of those, 5 of those, 20 of those. Okay, so now we have to make all of that cancel out. Okay, so we're going to take it and we can go ahead and eliminate whatever we can get rid of, like before. Okay, so we're going to have, we have water on both sides. Okay, yeah, so we can get rid of that. So we have 18 waters over here. That's still odd waters. And yeah, that's right. Okay, sorry, something was not looking right to me. So then we have our 10 electrons on both sides. Get rid of those. We don't need them anymore. We have 10 hydrogens on the other side, 16 on this side. So we can get rid of 10 hydrogens on both sides. Okay. I think that's as much as we can eliminate down on that. Something. I don't know. Something just looks backwards for some reason. I'm not sure what. Okay. So we have this here. Okay. So yeah. Then we could take this, and that ends up being our final answer. Don't need that. And then, so then we would take, oops, this here. So if it was basic, we have to put this. We have to get rid of the, whoops. We have to get rid of the hydrogen once more. So we're going to add our OH to both sides. So we have 6 OH minuses. Okay, so we add our 6 OH minuses. We can go ahead and see. Okay, so then got 6 OH minuses. These, like just like before, this is going to get rid of that. And this, in turn, combine them and make them 6 waters. Okay, and then we're going to be able to look at that and see that we have 18 waters over here and 6 over here. So we can go ahead and get rid of 6 waters on both sides. And there you go. That should be your solved reaction right there. Okay, so we're going to use the half reactions provided to give our standard potential for the following reaction. How much more do we have? May not get through all of these because we're bad at time. Okay. So we're going to look at this. It's more, oops. Okay, so we're going to have the equation here of cathode and anode. So we're going to use the half reactions to give the standard cell potential. So, okay, one of the things that they talked about, so your cathode, I don't know if you guys remember this, your cathode is going to be the one with reduction. So your cathode has the reduction reaction, and your anode has the oxidation reaction. I remember this just by like, this is a C and R are both consonants, so the consonants go together, and A and O are both vowels, so the vowels go together. That's kind of how I remember that. And yeah, so you're gonna have your E cell equals the cathode minus the anode, which, like we talked about, using the wrong thing. There it goes. Okay. So like we talked about here, that's this equation that we're using. That's here. Okay, cool. Use this equation. E cells cathode minus anode. And the cathode, we're going to have to figure that out. So which one we need to find out. There it goes. Okay, so our cathode has the reduction reaction. So which one's being reduced? Well, they made it kind of obvious with this one. It's going to be our iron because it has a +3 charge here and a +2 charge here. So that's the one that's being reduced. So, so we're going to have that one first. So when you look at the little chart that we had here, that chart at the bottom with the half reactions, find the one with our iron there. And if you went ahead and found the half reactions, that's the reaction it would be that it has listed there. And so that one is going to be first. So we're going to have 0.771 minus our anode. So our anode's going to be the other reaction. And you can see that this goes from negative to positive, so that's oxidized. And so we're going to look at that and find our chlorine on here. And that's going to be positive 1.36. So when we solve that, we're going to get our E cell value, which is going to be negative 0.89 volts, because those were volts too. I just didn't write it. And and that's spontaneous since that's negative, like we talked about earlier. Or non-spontaneous, I mean, because that's negative. Let me write that. Non-spontaneous. All right, so let's move on to the next one. Sorry I didn't write out the equations for those, but if you look at the equations on that little sheet right there, those are the equations that it'll be. Okay, so we're going to look at this reaction. Still see that. Okay, so for the following reaction, calculate the standard cell potential and then use that value to calculate the delta G. Okay, so first off, we have to find our standard cell potential. So same equation that we just did right here. Do that again. Oh, this is weird again. Okay. Okay, so we have that. So we're going to look at this. So our cathode, like we talked about, that's the one that's being reduced. So this is going from positive to 0, so that must be the one being reduced. So we have our lead on here. Look at that, and that's going to be negative 0.13. So E cell here. Negative 0.13. We're going to subtract the anode, so the one with oxidation reaction. So that's going to be our zinc, because that's going from 0 to 2. So we look at our zinc, and that is negative 0.76, negative 0.76. So when you do the math on that, you're going to end up with, oh shoot, I wrote the answer for that one up here. That's the one for down there. I just wrote the wrong one. That's 2.1. That answer doesn't even make sense up there. 131 volts. Sorry. Okay, so this one is our negative 0.89 volts. Okay, so now we're going to use that other equation here. And we go to that real quick. We're using, which one was that? This one right here. Right here. Okay, so we can go back up there. It's page 5. Okay, and use this equation now. Okay, so we need to find delta G. Okay, so negative, what is N? So we're going to look at this, and N is the moles of electrons that are being transferred. So we're having 2 electrons transferred from here, or from here across to there. So when you look at that, so that's going to be 2. Then we're going to have the Faraday's constant, which is our 9,000 or 96,500. I cannot remember what that unit is called for the life of me. I apologize. This one's, I can't remember what that's called. I'm sorry. Moles of E minus. Oops. Which that's our same unit from over here. There we go. Okay. And then times our E cell, which we just solved for. So that's our negative 0.89 volts. Whoops. The wrong thing. Okay. So then we're going to have this, and you can go ahead and do the math and solve for that one. And when we do the math, we come up with 171.8 kilojoules per mole. Yeah. Okay, there's that. This problem, let me see how much. Put that one. Show a few more. I think that problem is really similar to one we did. We'll go ahead and do it though. This session might just be a little bit long. If any of you are on here and you haven't sent me your name and UID, if you'll private message that to me, I'd really appreciate it. Thank you. And that way I can fill in our sign-in sheet. Okay. So we're going to use, we actually used this equation up here a minute ago. Not sure how far up. That one? Oh no, we didn't. We used a similar one, but not that one. So we're going to do this equation right here this time. So using the standard cell potential from the previous question, determine the cell potential at 25 degrees Celsius whenever the concentration of the lead ion is 4.6 molars and the concentration of the zinc ion is 1.8 times 10 to the negative 5 molars. So what we solved for up here was E cell. So we already have E cell. So E cell there. So our E cell was negative 0.89 volts. Okay, so we're going to subtract this. I'm just going to copy and paste that. Okay. N is going to be the same as last time, so that's our 2 once more. And our Q, remember how you find Q where you do the, because we're using the same equation that they had here. So it's the products over the reactants with that. So they gave us DN2 plus, so products over the PB2 plus over reactants. We're going to have to put this one over that to find Q. So that's what Q is going to be equal to. That'll be this one. Divided by this one, 4.6. I guess I got the more less of it again. Okay. And if you solve all your math out for that one, you're going to get your E cell, or your E, not E cell, your E is going to equal negative 0.73 volts. And then if you're trying to solve this, the log of Q, just so, whoops. The log of Q, when I solved that out, I got negative 5.47. So if that, you're trying to figure out where you messed up, if you go back and solve that one, that might help you out there. Okay. Electrolysis. I already have this in here for you. Control. Okay. Is the use of electrical energy to create chemical reactions used to drive non-spontaneous reactions. So, yep, you have that. How many kilograms of aluminum metal can be produced from a solution of, I think, yeah, from a solution by a current, yeah, can be produced from a solution of aluminum 3+ by a current of 1200 amps per a period of 15 hours. Okay, so what we're gonna do with that, your 1 amp or 1200 amps or whatever, so 1 amp is equal to one of the C, it's 1C over S. The C, it's the same one that was above that I can't remember what it is. I want to say they're called like Calhouns or something like that, but I can't remember for sure, so don't quote me on that. I apologize. Can't remember exactly what that's called. And so we're gonna have 1200 C's per second. We'll put these in parentheses. Okay. C's per second. Because we have that. Okay. Then we're going to go ahead and multiply that by our time to get rid of the number on the bottom there. or the seconds on the bottom here. So what do we have for time? We have 15 hours. But we need to have that in seconds. So we're going to multiply that by 60 minutes in 1 hour. And then 60 seconds in a minute. Whoops. Okay, so now we've gotten rid of our seconds there. And then we are going to use Faraday's constant to get rid of our C value. So to do that, we're going to use our, because it's going to be one mole E minus whoops, not yet. That's going to be divided by our 96,500 C's. Okay, so I got rid of that. So now we're at moles of E minus, and we need to convert that. We're trying to get to kilograms of aluminum, right? Okay, so we're going to multiply this by, we're going to go ahead and move that into moles of aluminum. So we're having aluminum metal going into Al3+. So that means we're having 1 mole of aluminum produced for every 3 moles of electrons. So we're going to have 1 mole of aluminum over 3 moles E minus. Okay, so now we have this in moles of aluminum, and we need to get it to kilograms. So we're going to multiply by the molecular weight that. So that's going to be our 26.98 grams per mole. If you look at a periodic table, per mole of aluminum. I'm just going to not type the aluminum. So now we have it in moles, and we need to get it into kilograms. Or we have it in grams, excuse me, we need to get to kilograms. So we have 1 kilogram per 1,000 moles, or kilograms, I mean. I bet if I got rid of all these spaces I put in here, that could be on the same one. I don't know. Maybe not. Oh, almost. Not quite though. So I'm gonna make that like a size smaller so that looks right. Okay, so you do all of that and you end up with 6.039 kilograms. Not quite. There we go. So then we have that. It's gonna be stubborn. Whoops, that is 0. There we go. Okay. So there's your final answer there. For the following reaction, calculate E and delta G at standard conditions when the concentration of copper is 2.2 molars and the concentration of zinc is 1.3 times 10 to the negative 3 molars. So go ahead and do that one, and then Yeah, that did. Right. Okay, cool. Go ahead and do this one, and then that was our last problem. We'll put this on the next page to make sure we have enough space. There's a whole other page there, so might as well. Okay. So for the following reaction, we're calculating that. So we need to calculate E and delta G. And this one. And they gave us that, so we don't even have to find it. Okay, so let's go ahead and do delta G because we have everything we need for that. So delta G looking at this equation right here. Okay, so delta G Yep. So delta G is going to be equal to what? Okay, so we have negative n. So when we look at our equation here, that's the number of electrons. So you can see the difference between here and here, that's 2 electrons, and between here and here, that's 2 electrons. So that's all we have to worry about. It's going to be negative 2 moles E minus. Go ahead and put that. Let's see. Okay. Then we're going to have the Faraday's constant, which is the 96,500 C per mole E minus. Okay. Then we're going to have our E cell value, which I guess we have the half reactions. We need to go ahead and find what our overall reaction would be with that. So we're going to do cathode minus anode. So our cathode is, remember, it's going to be the one with reduction. So positive to 0. So that's going to be a reduction. So it's going to be zinc minus copper. For that, no, it won't let me solve it over here. We'll go ahead and do. So we're finding our E cell. Go steal that equation, put it in here. So the reason you have to subtract the cathode minus anode is because whenever they give you the values in the table, the anode equation is going to be backwards. So if you go ahead and solve that, and you just look at it and go, okay, if you don't want to remember this, you honestly don't have to. You just add them together with the equations the right direction. So you see how, so we're doing cathode minus anode because you see this is on the left side of the equation up here whenever it's on the right side down here. So this is backwards. So that's why we have to subtract it. But if you don't want to remember that, if it's easier for you, you can just switch them the right direction, which would switch the sign on this to positive and do that. And you see that whenever we actually solve this, that actually works out. So if we have our E cell value, it's me cathode, so negative 0.7618 minus our anode, so negative 0.3149. So you know, see that ends up being positive, and if this was flipped, it would just be positive. So you can do it that way too, and that's fine. And that gets you a value of, right, oh, here it is. Okay, of negative 0.4469 volts. Okay, so now we have that value to go ahead and put it in here. So negative 0.4469 volts. Okay, so our delta G value is going to be, you go ahead and solve all that out. Here we go. Here we are. That's going to be 86.238 kilojoules. And so we have that. Now we need to find our E value. So our equation for E that we had down here is this right there. So here we go. Okay. All right, so now we have E equals our E cell, which we found is this right here, minus 0.0592 divided by N, which we just talked about up here. Yeah, that's 2. And then we're going to multiply that by the log of Q, but we don't know what that is yet. So they gave us zinc and copper. Oh wait, is that the same thing we just did? No, that's something else. Never mind. So gave us the zinc and copper here. So we do that. So it's going to be once more the products over the reactants. Oh, that's the reactant. I had that backwards. It's going to do 0.22 divided by the reactants. So it's right here. Okay. And if you solve all that out, you come up with your E value of negative 0.37161 volts. That's all I have for you guys. If you would like, you can ask me any questions. Yeah. Let me go ahead and end my recording.